initiation. So
Thank you.
please start.
Thank you, Nahu. So, thank you. First of all, thank you for the introduction and for the invitation to give a talk here at KIAS. So, I'm a postdoc based with the N3AS network at Berkeley, and as a part of it, currently I'm located at Northwestern University. So, the topic of today's talk would be essentially looking at the Dodelson-Widrow mechanism, which is a very interesting way of producing dark matter in the universe, and how it gets modified in the presence of new neutrino interaction, and whether we can have observable signatures of these interactions or not. These works, the talk would be roughly based on these three papers, which we put up in the archive in the last 1 year or so. And so feel free to interrupt me any point of time to ask any questions. So let's start with a lightning quick introduction of what we know about the standard model. Just a sec, let me get rid of this. Yeah. So we know that within the standard model predicts neutrinos, but the standard model does not really end up giving masses to neutrinos. So within the standard model, the neutrinos are massless. But then we have enough experimental evidence to know that the neutrinos are massive, and then they can oscillate amongst themselves. So they can change flavors. We also know that there are definitely at least 3 active light neutrinos. And although we do not know the masses, although we do not know the individual masses of the neutrinos, we know how the mass differences can be ordered. There are 2 possible options. So you can have something called the normal mass hierarchy, where essentially the mass ordering looks like this. So basically the mass eigenstate with the least content of nu e's would be the heaviest eigenstate, and the other 2 are organized like this, as you can see. So in this case, for example, the red band stands for nu e. So as you can see, nu 3 has the least amount of nu e's, and the others go on as it is. And similarly, you have something called the inverted mass ordering, where basically the one with the least amount of nu e's has the lowest mass. So these are 2 possible mass orderings, and we still don't know exactly which one our data favors. What we also know is that neutrinos interact weakly with the rest of the standard model. So they basically interact through the weak interactions, and interact through these interactions with themselves as well as with the rest of the standard model. The question we want to ask is that the only interaction that neutrinos have? From a theoretical point of view, we have had quite a rich phenomenology of neutrino interactions. People have thought of non-standard neutrino interactions, where neutrinos can interact with matter with interactions which are beyond what is predicted by standard model. So typically, such non-standard neutrino interactions are shown in terms of higher dimensional operators. So the most general 6-dimensional operators are shown through this kind of an operator. As you can see, you have the neutrinos interacting with fermions through different combinations of gamma matrices with some coupling, and it becomes operative at some scale. And this has been done for quite a long time. There was a recent conference also on this, and a lot of details have been collaborated in this interaction status report as well. So people who are interested can have a look at this. So the basic point is there are reasonably strong constraints on these kind of non-standard interactions of neutrinos from observations of solar neutrinos, atmospheric neutrinos, reactor neutrinos, as well as long baseline neutrinos. So we can do experiments where we can scatter neutrinos of matter, and that helps us to put quite strong constraints on these couplings per se. However, there are another kind of non-standard interactions that neutrinos can have. Neutrinos can have non-standard self-interactions. Essentially, what this means is you can write down an operator that looks like this. You have a neutrino coupled with some scalar, let's say, or even a vector, both are allowed. And what this allows you is that at the 6-dimensional level, it allows you to write an operator where basically you just have 4 neutrinos interacting with each other. Now, this operator is far more difficult to constrain because this operator affects only the neutrinos themselves. They do not affect the charged leptons. Of course, how you can write down this operator is a different question, and I'll talk about that later. But the bottom line is that once you write down this operator can in principle impact any process where a neutrino is present in the initial or the final state. What do I mean by this? So let us look at simple processes like the invisible Z decay. So you can have an invisible Z decay, but then the news at the end of the invisible Z decay can exchange a phi and then again get emitted. So this kind of process can add coherently to your invisible Z decay process, and this can change your invisible Z decay bounds. You can also have cases where the news would brem out a phi and change to another particle. Interestingly, if you want lepton number to conserve, if you look at this operator, phi has to have a lepton number. So phi would have a lepton number of -2, for example, What that means is if a final state nu emits a phi, it can turn into an anti-neutrino. So these kind of ideas have been used to put constraints on these non-standard self interactions. The most recent constraints have been updated in this paper. And essentially, as you can see, there are constraints from tau decays from these kind of operators, where basically any kind of phis emitted in the final state can change your tau decay widths. So this puts certain kinds of bounds. You can have bounds from decays of mesons, like d mesons and k mesons, which are shown out here. You can have bounds from invisible z widths, as well as pi meson and k meson decay bounds. The bottom line is that the constraints on these kind of operators are not very strong. So for a reference, the standard model weak interaction, which is G Fermi, would lie somewhere along this line from 10 to the 3 along a straight line. So even if you put in this, if you put in a coupling which is flavor universal, you would not even be rule out couplings which are as strong as the weak interaction, let alone interactions which are much stronger than the weak interactions. So these kind of operators particularly are quite difficult to constrain. You would, from a BBN perspective, you would expect the mass of the phi to be less than an MeV, or to be greater than an MeV or so. Anything less than tens of MeVs would be ruled out. So basically, you have these immense white area in the parameter space where you can lie, and you would be safe from all these bounds. Of course, as I said, building a model where the neutrinos only talk to themselves and not talk to the charged leptons can be quite tricky. And there have been quite a lot of exercises on this. One of the more recent ones has been tabulated in this paper, and you can have a look at it to see how you can write down models which only give rise to such neutrinophilic interactions. In this talk, we would be focusing on these kind of neutrinophilic interactions. The interesting part is, as I said, a large values of these non-standard self interactions are allowed within the neutrino sector. And this immediately brings about a large number of consequences. So although constraints from terrestrial experiments are not so easy to put, these kind of interactions can have very dangerous consequences for the early universe, for compact objects, and so on. So for example, a more recent work, this one, actually suggests that you can have very, very large couplings within these neutrino sector, and such strong neutrino self interactions can actually resolve the discrepancy that exists between the measurements of the Hubble constant through high redshifts as well as low redshift measurements. So if you put in very strong self interactions, you essentially suppress neutrino free streaming during the CMB, and this immediately drives the CMB Hubble constant value to the values that is preferred by the low redshift measurements. On the compact object size, this actually can have quite drastic consequences for core collapse supernovae. For example, within a core collapse supernova, we know that the neutrino density is very high. So as soon as the neutrino density starts increasing, these self interactions start operating amongst themselves. What it does is it introduces two time scales in the problem. So on one hand, you have the neutrinos talking to themselves through these very strong interactions. When I say strong interactions, I mean strong interactions mediated by phi and not the QCD. So QCD doesn't play any role in the talk that I mentioned out here. So what happens is you introduce two time scales. You have very strong interactions mediated by these non-standard phi particles. On the other hand, you also have the weak interactions operating where the neutrinos just talk to the leptons to standard weak interactions. And these two time scales can cause a change in equilibrium configuration in the star and lead to a large amount of entropy generation. And this has been explored quite a lot in a lot of papers. Also, it changes things like collective oscillations inside a supernova, which are primarily dependent on neutrino self-interactions. If you want to look at neutrino decays, these operators can also mediate neutrino decays, and this can put very strong bounds. Essentially, it can affect a lot of things in terms of compact objects as well as the early universe, and I have worked on quite a few of them. So what I will be focusing on in this talk is looking at how these self-interactions can actually help in freezing in of sterile neutrino dark matter. This is what's going to be the topic of this talk. And if you have questions about the other things, I can answer later on once the talk is over. So let's go back again to the first picture. As I just said, the standard model predicts at least three flavors of neutrinos associated with the three charged leptons. But the question that we still want to answer is, are these three flavors enough? Or do we have more flavors of neutrinos that we do not understand or we have not detected? Why do we want to predict more flavors? Is there a reason to predict more flavors? Well, there are four major suspects for this. Firstly, theoretical bias. As theorists, we like to introduce new particles if they help us to solve a lot of experimental anomalies. And for that purpose, having a new dark sector with little or zero interactions with the standard model is quite alluring. Secondly, there are quite a lot of short baseline anomalies in the neutrino sector, which actually can be addressed if you put in an additional neutrino which is sterile, which doesn't interact with the standard model, and which has a mass of around an eV and large mixing. So this can actually address a lot of these short baseline neutrino anomalies as well as the reactor anomalies. From a cosmology point of view also, there are advantages that you would have if you add in these sterile neutrinos, essentially from the point of view of so there are problems in cosmology if you want to match your theoretical predictions with that of the large scale n-body simulations that are done. So the simulations predict certain things which are not there in observations, and if you want to make them match, you would, one of the solutions is to introduce these kind of sterile neutrinos. So these are broadly some of the reasons why you might want to have an additional degree of freedom. And this also can be a very nice dark matter candidate, as we will see. So why is the sterile neutrino interesting? Firstly, from a theoretical point of view, the sterile neutrino provides a standard model with the right partner. Literally, it is the right-handed partner of the standard model neutrino, and it can be used to give masses to the neutrinos. So it's a very eluding candidate to give masses to the neutrinos. Secondly, the sterile neutrino can also be used to answer the baryon asymmetry of the universe through the leptogenesis mechanism. This is also a very well-studied mechanism. Thirdly, as what we will see in this talk, sterile neutrinos are possible dark matter candidates, as they can be used to solve such small-scale structure problems that I just talked about. And there are hints in terrestrial experiments. So let's look at these sterile neutrinos in a bit more detail. For simplicity in this talk, we would focus on two such species of neutrinos. We would call the nu A to be the active neutrinos, which have standard model interactions, and you have a sterile neutrino, which is nu S. And then you can write down a mass eigenstate as a linear combination of this nu S and a nu A with a mixing angle of theta. Now this immediately allows you to make the sterile neutrinos decay, because these sterile neutrinos can mix with your active neutrinos. So let's look at a typical Feynman diagram for a sterile neutrino decay. A sterile neutrino can mix into or oscillate into an active neutrino, and then this can decay into a photon and an active neutrino through such a loop diagram. Now, this process has been calculated quite long ago, like around 40 years ago or so. And the decay rate for this process roughly goes proportional to the fifth power of the sterile neutrino mass and the square of the mixing angle. The interesting part is these photons that would come from the decay of these sterile neutrinos can actually be detectable. Or on the other hand, you can say that if you cannot detect these photons, then you can actually put some bounds on this parameter space of the mass and the mixing angle of the sterile neutrinos. Also, if you look at a galaxy cluster or any other clusters, you might expect a lot of dark matter candidates in that area, and then radiative decays of the sterile neutrinos would act, since this is a two-body decay, would actually predict a line at an energy which is basically half of the mass of the sterile neutrino. So this theory has been there for almost 20 years. It gained a lot of impetus in the last 10 years or so when there were hints of a line which existed around 7.1 keV in this X-ray band, in the as was noted in this paper by Bulbul et al. And this line has been consistently observed in certain galaxy clusters or so. However, there are also contrary reports by other groups which have not seen these observations. So they have basically done blank sky images between stars in our own galaxy. And from that, they say that this line does not exist. So the bottom line is this is still not completely resolved. We don't know whether this line exists or not. But this gives a very nice impetus to the study of sterile neutrinos, because if this line actually exists at 3.5 keV, then that immediately points to a sterile neutrino at around 7.1 keV. And so it's like this excess would be given by the radiative decay of the sterile neutrino. So then the question is, let's assume for the time being that these sterile neutrinos indeed exist and they can give such lines. But then how do you produce these sterile neutrinos in the first place? So cosmology does not allow you to have the sterile neutrinos to be in thermal equilibrium with the standard model particles, because cosmology predicts the amount of primordial deuterium and helium in the early universe, and that tells you the amount of radiation that you can have in the early universe. Now, if you have the sterile neutrinos to be in thermal equilibrium with the standard model particles, this immediately infuses more energy into the plasma bath, and then that screws up your entire BBN calculations. So then what it says is you cannot have the nu S to be in thermal equilibrium before BBN. So you must produce them non-thermally. So you must start with a very small mixing angle and gradually produce them so that they're never in thermal contact before BBN. So how do you go about this? The idea is very simple. You start with a universe where there are negligible amount of sterile neutrinos. You only have active neutrinos. But then because the neutrinos oscillate, each mass eigenstate is a linear combination of an active neutrino and a sterile neutrino. Now, as the universe evolves, the active neutrino keeps on oscillating into the sterile neutrino and back and forth. However, the active neutrinos have one advantage which the sterile neutrinos don't have. The active neutrinos, let's say the nu E, would actually interact with the electrons in the bath. And at certain points of time in this oscillation, the active neutrinos would undergo an interaction with the electrons, which basically only affects the active component of the mixture and does not affect the sterile component. So over a period of time, the sterile component starts growing, whereas every measurement keeps on resetting the flavor to the initial condition again. So your flavor evolves to a certain point, a measurement takes place, the active neutrino composition is again reset, whereas the sterile composition starts growing. And this gradually builds up a non-trivial fraction of these active neutrinos, of these sterile neutrinos. And this would ensure that the sterile neutrinos are not in thermal equilibrium, and it can produce a certain non-thermal population of the sterile neutrinos. Now, this roughly is what the Dodelson-Widrow mechanism predicts. It allows you to produce the sterile neutrinos collisionally through oscillations of these active neutrinos into sterile neutrinos and can evade all the BBN bounds. So that's nice. So this is again, all I told you was a nice story, but then the question is, can you define it mathematically? Can you write down equations which can do this thing? So it turns out you can write down semi-classical equations which exactly do this thing. You can do a more sophisticated analysis by looking at quantum kinetic equations, but we don't want to do it out here. So let's look at the time evolution of the sterile neutrino distribution function. Now that essentially is a function of three different parameters. So as you remember the story from here, so you need active neutrinos to oscillate into sterile neutrinos, and every once in a while you need the active neutrinos to undergo an interaction of this form so that they can oscillate back into sterile neutrinos again. So in order to understand the time evolution of these sterile neutrinos, you need the active neutrino distribution function. You need an expression for the probability of converting the active neutrinos into sterile neutrinos, which takes into account these oscillations. They have to be averaged over one mean free path of these oscillations. And then you also need some non-trivial interaction rate. These interactions rate has to be also scaled with the Hubble parameter to make sure that they're always in equilibrium. And then the product of these three would give you the evolution of these sterile neutrinos and production of them. So how do you calculate the oscillation probability? So as I said, the oscillation probability is averaged over one mean free path of these active neutrinos. So they are essentially a function of three parameters. They're a function of the mass square differences. Now, for the parameters we are considering, the mass square difference is essentially just given by the sterile mass square difference. They are a function of the mixing angle in vacuum. They are a function of the rate at which these interactions happen. So the active neutrinos can undergo weak interactions. So these rates are captured by this gamma. And they are also a function of the potential that the neutrinos feel. So essentially, as the neutrinos travel through matter, they can feel forward scattering potentials because of Feynman diagrams of this form. So a neutrino can undergo forward scattering with a background fermion, and this leads to a potential. Now, this potential can have two components. This can have a component which is essentially proportional to a finite temperature piece, and you can have a component which is proportional to a finite density piece, which essentially is proportional to the number difference between the fermions and the antifermions in the matter ensemble. Now, since the early universe is supposed to be isotropic to a very good approximation, you can put this quantity to zero, and the potential is essentially governed by the thermal piece. So the other interesting part out here is that if you look at the the conversion probability has this interaction rate factor in the denominator. So what this tells you is that if you go to a regime where these interaction rates are extremely high, this probability goes to zero. This limit is known as the quantum damping limit, because what it does is it tells you that if you are in a regime where the interactions keep on happening very fast, it corresponds to a regime where you're continuously measuring the flavor of the neutrinos at every point of time. Now, because this measurement happens so fast, it kind of freezes the nu E component of the mixture and does not let the flavor to evolve. So then that means that there is no flavor conversion to start with, because the interactions are so fast. And in this limit, everything goes to zero. So you cannot go to very high regimes of interactions. There has to be a sweet spot where you would start converting these active neutrinos to sterile neutrinos. Now, this is the governing equation that you're interested in. And once you solve, you can calculate the interaction rate for the standard weak interaction out here. You can calculate these potentials by just computing these diagrams, and then that allows you to compute what the sterile neutrino distribution function in the early universe looks like. Now this is exactly what Dodelson and Widrow did in the early 90s, and what this tells you is that in order to satisfy the relic density of dark matter that is observed, you need to lie on this black line out here. So if you lie on this black line out here, so this is the plane of the sterile neutrino mass and the mixing angle. And if you lie on this black line out here, you can actually produce all the dark matter that is observed in the universe. Now that's good. So it does predict you, it does give you some region in the parameter space where you can produce the dark matter lines in the universe. However, this line immediately gets into tension with the fact that these sterile neutrinos can actually be observed through their decays from into photons. So if you look at this kind of a process, as I say, so the sterile neutrinos can decay into a gamma and an active neutrino. Now these gammas get redshifted over time and they can form a distribution of diffuse background X-rays. And there are measurements of these diffuse background X-rays by different telescopes. So you have measurements by integral, you have measurements by XMM Newton and so on. And what they do is they tell you that if you had these sterile neutrinos and they would produce these gamma rays, then essentially this entire blue shaded region would be ruled out. This immediately puts the Dodelson-Widrow mechanism in a lot of tension, because it says that more than half of the parameter space that it predicts, which would be the dark matter relic density, is already ruled out by non-observation of these X-rays. Also, if you look at this plot, there are a couple of other things that are interesting. So there is this point out here, which, as you can see, exactly lies on the 7.1 keV line. So it also, this measurement of these X-rays also says that if you want your sterile neutrino to form the 7.1 K, to form the line at 3.5 keV, the parameter space point has to lie exactly out here, which also is partially in tension with these X-ray observations as well. There are other bounds also. There are bounds from Katrine, which is basically a beta decay experiment. So Katrine tries to measure the effective mass of the neutrinos, which essentially is also proportional to the number of generations of mass eigenstates that you have. So if you have 4 neutrinos, then Katrine would predict a different bound as compared to what it would predict if you had 3 neutrinos. So that rules out some regions of parameter space. And then there is a more fundamental bound that comes from the fact that these neutrinos, sterile neutrinos, are at the end of the day fermions. So they obey Pauli exclusion principle. So you cannot really stuff too many of them in a given dwarf galaxy. So that rules out regions of around 2 to 3 keV. More stringent Lyman alpha bounds and so on can exist, and they almost rule out regions up to 10 keV. Overall, what it says is that the entire parameter space that is predicted by this Dodelson-Widrow line is ruled out from observations, be it from X-ray observations, be it from dwarf galaxy observations, or so on. Now, so that means that the parameter space by Dodelson-Widrow mechanism is in tension. And if in order to make it survive, we need to push it to more and more bottom space of the parameter space. So this line has to move out here for it to survive. Now, over the years, a number of mechanisms have been put forward to do this, and most of them introduce some kind of new physics or the other. One of the more popular mechanisms that was introduced a few years later was the fact that you introduce a finite lepton asymmetry in the universe. So if you remember, as I said, we typically put the finite density part of the potential to 0 because the early universe is supposed to be isotropic and homogeneous. But then if you put in a finite lepton asymmetry, you can hit a resonance out here because of the finite density part, and this can immediately help to push this line below. However, this mechanism suffers from one major problem, is that it requires a very large lepton asymmetry for this mechanism to survive. And then you have to first, such large lepton asymmetry has not yet been observed. And secondly, you also have to survive, you also have to live with the fact that you have a very large lepton asymmetry, but you do not have such a large baryon asymmetry. So there are a lot of issues that arise from this mechanism. So then the question that we want to address in this work is that, can we push this line further below without introducing a finite lepton asymmetry? Are there other new sources of physics that can do this? Now, this is where we start introducing these neutrino self interactions. As I said, these neutrino self interactions are they are essentially not very well constrained. So in principle, you can have these self interactions to be much stronger than the ordinary weak interactions. So let's take a very effective model for these weak interactions. Let's take a model where essentially you have an operator of this form. as you would recognize, it's the standard Weinberg operator, and that is married with this new scalar phi. And we want this phi to have a lepton number so that our neutrinos are Dirac throughout. So essentially what this tells you is that you would need phi to have a lepton number, for example, of -2 if you want this operator to be lepton number conserving. Now, once electroweak symmetry breaking goes through, this operator predicts an operator of this form, which essentially allows the neutrinos to talk to each other through this scalar phi. Now, why do we want to introduce this coupling in the first place? How does this help us? So let us go back to this plot again. And as I said, we want this line to shift more and more down in the parameter space. What that means is that we need a smaller and smaller mixing angle to satisfy the relic density of the universe. Now, if you look at this equation, the relic density is essentially given by the number density of the sterile neutrinos that you produce. And that is a function of two main quantities. It's a function of the rate of the reactions that the active neutrinos undergo and the mixing angle. Now we want to make the mixing angle become smaller. That automatically implies that we want to make these interaction rates go up. And that's what we do. So the relic is essentially a product of these two quantities. If we want the mixing angle to go down, we need to amp up the rate. And so instead of the weak interactions, we introduce these new interactions, which would be much more dominant than the weak interactions. And then they would allow the active neutrinos to be produced through that interaction rate. And then you can convert them to sterile neutrinos with a much smaller mixing angle. Now, of course, these kind of self-interactions again have the same kind of bounds that I discussed before. And there are constraints from labs, which are essentially pion and meson decays. There are constraints from invisible decays of the Higgs and Z's, which lie somewhere out here in this parameter space. There are constraints from BBN. You do not want these mediators to be too light, else you screw up BBN. But what this tells you again is that you have this large parameter space, which is allowed, which lets you survive and which lets you have these strong self-interactions. So this automatically opens up new production channels for sterile neutrino dark matter. So if you want
excuse me.
Yes.
May I ask a question?
Yeah, sure.
About this figure? I suppose this G phi will be lambda phi in the first equation, right?
Yes.
And yeah, and once you suppose this coupling is related to a seesaw, I guess it's related to the theta in the previous slide, right? Mixing between the active and sterile neutrino.
No, so you don't want this phi to get a web. So you don't want this to give any contribution to the neutrino masses.
Oh, okay. So you, I see.
So
it's a completely different.
Get it. It's a complete zero. So it's not constrained by the neutrino mass.
Okay, I see. Yep. Thank you.
Okay, good. So then to summarize, what is it that we have done in the context of the Dodelson-Widrow mechanism? So the Dodelson-Widrow mechanism says that within the standard model, you have interactions of this form. A new E hits a E and produces a new again, which oscillates into a new S. What you do is you add to this these kind of self-interactions. Now, of course, there are no limits on the mass of phi as such, as long as you are in the right coupling regime. So for these self-interactions, there are two possible production channels. You can go to the regime where the phi is quite heavy, and then this reduces to a 4 Fermi-like interaction. Or you can go to the regime where the phi is light enough to be produced on shell, and this produces an additional channel where the sterile neutrinos can be produced through on shell decays of these phis. So it adds these two new interaction channels, and then this gives you the lever to change the rate so that you can satisfy the relic density. Now let's look at the limit where the phi is greater than order 1 or order 10 MeV, so that you never worry about BBN bounds. I'll go to the other limit slightly later. So in this limit, now if you remember, this was the equation that we talked about. So you can vary your mass, your coupling of the phi and the mass of the phi, and you can solve this equation numerically. And you can ask the question that under what conditions or under what values of these parameters do you satisfy the relic density of the universe? And you get this very interesting S-looking curve. Now this is not very intuitive immediately. So you don't understand why does it have a non-monotonic dependence. If you go above this curve, you have an overabundance of dark matter. If you go below, you have an underabundance of dark matter. So we try to understand or explain this curve through analytic means. So how do we do that? We look at this equation, and then we try to look at different limits in which you can actually solve this equation analytically. It turns out that that is indeed possible. So if you look at this equation, there are essentially three major timescales involved in this equation. The first timescale is essentially when gamma over h is equals to 1. So that tells you the regime at which these interactions actually decouple. So when gamma over h becomes less than 1, these interactions are not in equilibrium anymore. The second regime is essentially when this delta is equals to the potential V. That works almost like an MSW resonance. So what that tells you is that in that regime, this term entirely goes to 0 and the mixing angle is unsuppressed. So you start reaching a peak production regime. And you also have a third time scale where essentially the temperature is of the order of the mass of the mediator, and then you cannot produce these mediators on shell for a lower temperature. So these are the three time scales involved in the problem. And it turns out that the different shapes of this curve essentially corresponds to different hierarchies of these three time scales. Let's try to understand them one by one to see if we do understand these three shapes carefully. So the first part, let's look at a point on this scale, this point A. This essentially corresponds to a heavy mass and a large coupling limit. It turns out that this is nothing but the Dodelson-Widrow mechanism, which is amped up. So let's look at the right-hand plots out here. So what these plots show, these three panels essentially show you the gamma over H ratio for the three prospective cases, A, B, and C. It shows you how the effective mixing angle varies, and also how the function, basically the distribution function varies as a function of Z. Z is a correspondent for time. It's just defined as 1 MeV over the temperature. So it gives you how that, so as Z increases, time increases. So for case A, essentially, because the mediator is quite heavy and the coupling is heavy, the first time scale where the mediator cannot be produced on shell is reached first. So the mediator is always off shell. Then you reach a time scale where the mixing angle is unsuppressed. And then finally you reach a scale where the reactions fall out of equilibrium. So as you can see, peak production essentially, so this peak is essentially giving you the peak production. So the peak production essentially happens around this time scale T delta equals to V, and it happens via scattering of an off shell phi. And this is the peak production is reached when the mixing angle is essentially unsuppressed. So the second scenario, if you look, so let's look at the third scenario first. This is more complicated. If you look at the third scenario C, this scenario corresponds to a case where the mass of the mediator and the coupling is quite small. So in that case, what happens is that first you reach a scenario where the delta is where your mixing angle becomes unsuppressed. So you have the vacuum mixing angle, and then the mediators gradually cannot be produced on shell. So eventually the major production comes through on shell exchange of phi, essentially between these two time limits. And the third scenario where is a more complicated scenario where you have an intermediate mass and an intermediate coupling. And what happens in this case is that although the phi's can, so scattering can still happen through production of an on-shell phi because the phi is light enough to be produced on-shell. But then the reactions fall out of equilibrium even before you reach peak production. So this is the hierarchy that governs it. And then in that case, as you can see, your peak production happens even when theta is suppressed. So you are in a regime where theta is still not the vacuum value and your peak production is still suppressed. Peak production still happens. So if you try to solve this equation analytically in these three limits, taking the proper limits of each of these quantities, you would see that there are three parametric dependencies of the dark matter relic density. So for case A, it essentially depends as this quantity. For case B, it depends as an inverse of lambda m5 function. And for case C, it depends like this. And this very nicely predicts analytically what these three slopes should be. So the dotted lines are basically analytical predictions, and the solid line is a numerical prediction. As you can see, this gives you an excellent fit to the numerical results. So once we have understood this thing, once we understand why this shape is and that this shape is correct, now we ask the question that, okay, so this is for a given value of the sterile. So this, for example, was a given value of the sterile mass and the given value of the mixing angle. Now we can run it over a large range of the sterile mass and the mixing angle and ask for which values of lambda and phi do you produce the correct relic density. So essentially what that means is, if you look at this plot, this was for a single value in the m sterile mass and the sterile mixing plane, and then you produce these kind of plots for a large grid over the sterile mass and the mixing plane, and then you ask the question, in which range do you solve the relic density. What we find out is that while the Dodelson-Widrow mechanism was just predicting this black line for the relic density, in presence of these self interactions, you have this entire region between the red shaded lines that open up. So you open up a large amount of parameter space below the Dodelson-Widrow mechanism, essentially because you start introducing large self interactions. And surprisingly, you also open up more parameter space above the X Dodelson-Widrow line, because there are regions in the parameter space where the potentials interfere destructively, and then that opens up more parameter space above this line. So instead of this line, now you have this entire region where you can satisfy the relic density for different choices of the m phi and lambda phi mass. And in principle, you can also get a value of m phi and lambda phi which satisfies this specific point, which is the one for the 3.5 keV line. So if you actually believe that the 3.5 keV line exists, in this model, you can find a combination of m phi and lambda phi value that satisfies this particular parameter space. You're not allowed to go into these shaded regions because they end up overproducing and underproducing dark matter. So in this specific model, you can actually end up producing the entire relic density of dark matter by choosing specific values of lambda phi and m phi. But then, as I said in the beginning, if you look at the Sheaf-Fuller mechanism, the Sheaf-Fuller mechanism has one major problem, that it cannot be experimentally tested. It requires a very large lepton asymmetry. So the question that we ask out here is that, can you test such self-interactions in our model? And it turns out that parts of this parameter space which can produce the right relic density can actually be probed by accelerated neutrino experiments. How so? So let us look at the bounds on these spaces. It's the same parameter space. You have these orange line which satisfies the relic density. And then what are the bounds on these lines? So you of course have the standard BBN bounds if you go to two low masses of this M phi. This is the bound that exists. You have bounds from meson decays. Above this triangle, you essentially end up having the sterile neutrinos decay earlier than the age of the universe. So you don't want to lie out here. And then you have this very interesting bound that comes from DUNE. Why does this bound come? So DUNE essentially looks at interactions of the sort where they fire a new, let's say they fire a new mu beam at a target. They fire a new mu bar beam at a proton target, and they try to see what the outgoing particle is. However, if you have these kind of an interaction and the phi carries a lepton number, you can have a process where the new mu beam emits a phi in the initial state and converts to a new mu bar. And this would produce a positive sign lepton because a new mu bar interacts with the proton. So what it does is it ends up producing the wrong sign muon in the process. So typically in absence of phi, you would expect this guy to be a mu minus, but then because the phi carries lepton number and this actually changes this to a new mu bar, it interacts with the protons and produces the wrong sign lepton number. So you can use the far detector of DUNE to actually see what this process is. And what this for low mass phi, you can actually get a large amount of missing PT for like missing transverse momentum if these phi's are emitted. And this immediately can be used to put bounds on this parameter space. So this essentially rules out this entire region, or rather DUNE in principle can probe this entire region of parameter space through these kind of processes. This is calculated in more details in these couple of papers. And what this shows you is that there are regions of parameter space which can be probed by DUNE. So this interactions are not completely without experimental probes, and you can try to rule out these models if for example DUNE can do it, and even other detectors like Minos and Miniboon can also try to probe these regions. So as of now, I was focusing on this region where the mass of the mediator is always large enough to evade BBN bounds. But the next question is, can you actually go to lower masses and not get into trouble with BBN? So this forms the second half of the talk. And it turns out that you can actually go to this limit where you are in a regime where the mass of the mediator is sub MeV, but you can adjust your couplings in such a way that you would still not run into trouble with BBN. So how do you do that? So let's look at this. So the algorithm for doing this is simple. So let's look at this cartoon on the top. So this is how time goes. So at certain point you have VBN happening, at certain point you have CMB happening, and there is a large time scale like of 6 orders of magnitude temperature difference between these two epochs. And the idea is that you start with a scenario where there is almost negligible phi population in the early universe up until BBN. So these phi's are almost never populated up until BBN, so you need very tiny couplings. Now the couplings are such that the phi's gradually start getting populated around BBN, but they're always out of equilibrium, so they never run into problem with Big Bang nucleosynthesis, and they eventually come into equilibrium with the neutrino system after BBN. So there is no measurement out here that tells you the amount of radiation that is out here. However, CMB can still kill you. So you want the phi's to decay before CMB. So then the game is this: you adjust your coupling such that the phi comes into equilibrium after BBN, and the phi also decays back to neutrinos before CMB. So this would still allow you to evade the BBN bounds. But of course, there would be some constraints on these kind of scenarios from the measurements of ineffective both at BBN and at CMB. And this is what we want to study. So let's look at one of these plots out here. So the only difference between two is in one case it's for a real scalar, in the other case it's for a complex scalar. So a complex scalar has one extra degree of freedom, and so this would have a factor of 2 changes in the bounds. But let's not go into that. Let's look into this plot first. So what we show out here in these lines are essentially the bounds on delta n effective that comes from this kind of a scenario. So if you allow the phi to be produced in such a way that it comes into equilibrium after BBN, you, of course, it's produced around the time of BBN, so it starts changing some amount. So it starts changing delta n effective at BBN also to some extent, but it shouldn't change it to an extent that it's ruled out by experiments. So, for example, Planck so from bounds from so for example, bounds of on helium and everything rule out delta n effective greater than 0.5 roughly at 95% confidence level. So if you look at this plot, this is the contribution of delta n effective from the phi equilibrating around the time of BBN. So this shaded region gives you a delta n effective of 0.57, for example. And then these lines are delta n effective of 0.3 and 0.01 and so on. So these contributions are tiny enough that they are not ruled out by measurements of helium. So if you look at very low masses of sterile neutrinos, masses of around 2.5 keV, 4 keV, or 7.5, 7.1 keV, which are very close to the Tremaine gun bound limit, the phase space limit, you see that there are regions of parameter space which are still allowed, as long as you are outside this shaded region, which predicts a delta n effective which is greater than 0.5, and you can still survive from BBN bounds. Of course, because the phi decays to neutrinos before CMB, there are also constraints coming from the delta n effective CMB, and these constraints are a little bit more relaxed. So, for example, around delta n effective of 1 is still allowed. For being on the safe side, we took delta n effective of 0.9 to be something that can be ruled out, but then smaller values are still allowed. So again, this shows you that values, if the sterile neutrino mass is as tiny as 4 keV or 2.5 keV, you're still allowed to have these parameter spaces being open, and you can in principle survive, but then there have to be experiments which have to probe these very small delta n effective. Also, so the reason why we find this interesting is that the upcoming CMB S4 experiment can actually probe very tiny values of delta n effective to like a sub-percent precision, and then we expect that these kind of models can actually be probed by the CMB S4 experiment. So how do you probe this thing? So it turns out that, let's say I look at one of these curves, the 2.5 keV. This has a very interesting shape. So it comes out like this, and as you go to lower and lower values of the masses, as the masses come closer, so as the mass of phi comes closer to the mass of the sterile neutrino, the lambdas have to increase in order to produce the same amount of relic density of dark matter, right? Because there is a phase space suppression happening because m phi is equals to m nu. So in that case, these curves have an upturn at a certain point where the phase space suppression kicks in. On the other hand, if you look at these contributions to delta n effective, these contributions essentially are proportional to the product of lambda and m phi, and they are these straight lines. So for each value of m nu, for example, for let's say 2.5 keV, there are lines of delta n effective which give you the minimum delta n effective that would correspond to this line. So if we take the line that touches this point, that would correspond to the minimum delta n effective at CMB and at BBN, that would correspond to this particular dark matter candidate. And if we can find out that particular minima, then that would be the minimum delta n effective that is needed to be probed to rule out this particular model. So how do we go about this? What we do is we take certain mass of dark matter, let's say either 2.5 keV, 4 keV, or 10 keV, masses which are in conflict with BBN if the couplings were large. But now we go to very low coupling, so we can evade the BBN constraints through this way. And then we look at the corresponding X-ray bounds. We look at the corresponding X-ray bounds that exist for these masses of dark matter, and we look at the maximum mixing angle that is allowed for a given mass of dark matter. So for 2.5 keV, let's say we look at the maximum mixing angle that is allowed by the current X-ray bounds. So for that mixing angle, we look at the minimum delta n effective bounds that can be imposed from CMB or BBN. That essentially is calculated by looking at the line which touches the minimum point of this curve. And that tells you what is the minimum delta N effective for a given mass and the maximum mixing angle that needs to be probed to rule out these models. And this is what we find. So the shape is still very complicated and we're still trying to understand this shape, but the idea is the following. So let's look at the blue lines. That's delta N effective contribution to BBN. And what this tells you is that if you go to very, very low masses of the scalar, you essentially do not end up producing them before BBN, and the bounds on BBN are almost negligible because the couplings are also extremely tiny. However, if you go to larger masses, then you end up producing them up to a maximum amount, and the contribution to delta N effective remains fixed. And in between, there are some weird behaviors which essentially depends on a lot of nonlinear factors and is difficult to understand. The corresponding behavior from CMB is also similar, excepting that there is a minimum bound on CMB that you can probe, because at some point you have to thermalize these scalars after BBN and the scalars have to decay again. So then that gives you a certain minimal delta N effective that you can probe. So for example, with the current X-ray constraints, you can probe a delta N effective in BBN that lies between 0 to 0.57. That is something that CMBS4 can and for CMB it can probe a delta N effective that ranges between these numbers. So these are numbers that CMBS4 can actually probe, and this makes it quite interesting. If you go to future X-ray constraint telescopes like Athena and so, which actually put much stronger constraints on the mixing angle, then in principle you can probe even larger value of delta N effective, because Athena essentially rules out even larger values of mixing angle for a certain mass of these dark matter. And then for a smaller mixing angle, you need larger energy density in these scalars to produce them. And so the delta N effective contribution to them becomes higher. So in principle, you can probe large values of delta N effective through the upcoming CMBS4 experiment and rule out these parameter spaces completely if you want to. So this model in principle is completely testable even to very low masses of the scalar. So what this tells you is that if you want these neutrinophilic interactions to be mediated by a scalar, there are quite a significant region of the parameter space that can actually be probed by different combinations of terrestrial experiments as well as cosmological experiments. And at the same time, they basically give you models which can allow you to produce dark matter consistently all over this range. They allow you models which can predict the 3.5 keV line, and at the same time they have quite a good testability. Now, the last part, so before I conclude this part of the talk, this gives you the big picture. If you remember, the first part of the talk essentially focused on this region where we had this S curve, and these are the constraints. Now, in principle, you can draw this curve to even lower masses of the scalar. You can draw it to even as low values as a few keV, and this is the upturn that you all saw in this plot. And it's this region that we still don't understand. We are working on trying to understand it. So essentially the reason why we use dashed lines to draw this region is that the two cosmologies that operate in this region and this region are quite different, because this region refers to very heavy phis which never thermalize with the plasma, whereas this region refers to phis which thermalize after BBN. This is basically the joining region where the phis behave in a little weird way, because they start gradually thermalizing with the plasma, and then this interpolation is not theoretically accurate. One needs to do much more precise modeling to understand this interpolation and how this goes over. But modulo that, we have a big picture which tells you how the lines of relic density would look like in this parameter space and what are the different constraints that can probe these kind of interactions. Now, this is all with a scalar. The last part of the talk, the last 5-10 minutes that I want to spend are on if you want to do a similar story with vectors. Can you have similar interactions with vector mediators? So the chain of arguments that I said can easily be used for vector mediators as well, because vector mediators can also give rise to neutrinophilic interactions. And in principle, the bounds arising on these vector mediators can be stronger because vector mediators are massive. And in this case, they have an extra degree of freedom that the scalars don't have. So they have a longitudinal degree of freedom. So in principle, if you look at different kinds of constraints, there are extra bounds coming from an extra decay mode. Essentially, this longitudinal degree of freedom acts like an extra decay mode. And this can give rise to extra constraints on your model. So for concreteness, we consider three very popular vector models. The first one is a neutrinophilic model. The second is the L mu L tau model. and the third is the V minus L model. You can choose any model that you like. We just show these three models because the bounds on arising on these models from different processes are very well tabulated. So again, I iterate this. The physics governing the creation of dark matter in this is exactly the same. You have self interactions mediated by vectors. These self interactions are stronger than your weak interactions, and they allow you to produce the dark matter. They allow you to produce active neutrinos more through these self interactions, and then these active neutrinos can convert to sterile neutrinos. The only difference is these interactions are mediated by a vector as opposed to a scalar. So let's look at them one by one. So the neutrinophilic vector, essentially the interactions look like this. This is the vector equivalent of the Weinberg operator. As you can see, it looks like an LH square, but it's mediated by a gamma. And this essentially leads to an operator that looks like this. Of course, there's this other difference, that as opposed to the scalar, the vector operator has to look like this, where you have a nu bar and a nu. So these vectors would not have any lepton number as opposed to the scalars. So now again, we try to look for cases where you can solve the relic density of the universe. These are these S curves that I also talked about before. We look at two possible cases. So a lower limit, which is roughly this 7.1 keV, because we know that if it's order a few keV, then you're already in tension with these Tremaine gun bounds and so on. So we don't go to lower masses. So this is what corresponds to this gray line out here. And we look at a higher mass, which is of the order of 50 keV, which is this guy out here. And for this, we try to see what are the different bounds that can exist on this. The bounds are again very similar channels. The only difference, as I said, is if you look at these cases, for example, the H2 nu bar V, or even these meson decays, you have this 1 by mv square kind of a behavior, which essentially arises from the decay of the Higgs, or in this case, the mesons, to the longitudinal degree of freedom. So this gives you this extra 1 by mv square kind of a behavior. So this makes the constraints more tighter. And there are other bounds from decays of Z bosons, decays of exotic mesons. There are bounds from supernovae. There are bounds from BBN. And also there are bounds from experiments like DUNE, where they essentially look at missing transverse energy due to this V being emitted. Now, all these bounds essentially rule out a large part of this 50 keV parameter space, whereas the 7 keV is still allowed, and anything in between is still allowed. So this is the most vanilla scenario, where you just have a neutrinophilic interaction. You can try to make it more generic by saying, let's say the vector mediator is an L mu L tau vector. So now there are more interaction channels open. It can interact with a muon, it can interact with a tau on, and these are the neutrino interactions. This, of course, puts a lot of extra constraints on your model, because there are extra interaction channels available. This vector now talks to more standard model particles. So there are more bounds on this. So again, you have the two standard parameter lines. You have the 7.1 keV and the 50 keV. Now the bounds are far more complicated. So you have bounds that arise from basically trident interactions. You have bounds that arise from beam dump experiments, like beam dump experiments and so on, like SHIP and so on. And then you have bounds that arise from electron positron collider experiments. And then this is the G minus 2 line, for example. And all these things can actually rule out the 50 keV line completely. Upcoming experiments like the NS64 experiment, or the SHIP experiment, or even the DUNE multipurpose detector can also probe this 50 keV, the 7.1 keV, and it can in fact rule out this line completely. Another model actually can be constructed, which is essentially taking the vector meson and charging it under a B minus L. So this is also very similar. You have interactions with all the possible leptons as well as the quarks. So the bounds on this are actually stronger. So you have bounds from neutrino electron scattering, because in this case you can actually couple to the electron. So there are bounds on neutrino electron scatterings from CHARM and Texono and so on. You have electron positron constraints from Bell and Babar, which essentially rule out a large part of this parameter space. Then you have beam dumps and LDMX and phasor, which also rule out almost the entire parameter space. So what the crux is, that the more stuffs you couple your vector meson to, the more you end up ruling out this parameter space, and you actually can probe these regions quite well if these vectors are coupled to any kind of current, like a B minus L or an L mu minus L tau. So this brings me to the end of my talk. So in summary, what I tried to propose out here is that a model with where the standard model is essentially appended with sterile neutrinos, and then you propose a new interaction among the sterile neutrinos, which is much stronger than the standard model weak interactions. Now, these new interactions can either be mediated by a scalar or by a vector, and their masses can vary between a few keVs to tens of GeVs. So these models can actually allow you to produce your sterile neutrinos via these new interactions and then oscillations. So essentially, these stronger interactions also help you to remove all the tensions that exist with the standard Dodelson-Widrow mechanism. And then if you believe in the 3.5 keV line, this can also be used as a candidate for the 3.5 keV line. And finally, these interactions are testable. You can actually probe them using current and upcoming neutrino experiments. So in a nutshell, this is what this does. You produce these sterile neutrinos through new interactions. These can decay via X-rays, and you can probe them through cosmology. And you can also probe them in terrestrial experiments in the near future through different kinds of neutrino experiments. So thank you.
Thank you very much for the nice talk. And is there any questions?
I had a question about B minus L model.
Yes.
Which go back to one slide. Yeah. I think you didn't mention about the sterile neutrino sector, but if you consider this sterile neutrino as a right-hand neutrino, then B minus L also couples to this sterile neutrino sector. So eventually the mixing angle dependence doesn't appear. Is that right?
Can you repeat this argument?
So in the B minus L case, so for instance, those two black and gray lines, you also shown the mixing angles, but
yes.
If the sterile neutrino also couples to B minus L, oh, this is not B minus L, by the way.
Oh, sorry. Yeah, this is sorry.
Yeah. So if the sterile neutrino doesn't couple, the sterile neutrino couples to B minus L gauge boson, the dark matter production doesn't depend on the mixing angle.
If it couples to the B minus L.
Yeah, because sterile neutrino directly can directly be produced.
Right.
Yeah,
so that would be in the lower. That would be in the in this regime of the parameter space, where the B minus L gauge boson can automatically decay into a pair of active neutrinos, one of which oscillates into a sterile neutrino.
That's also one channel, but there are several others.
So you are in a scenario where you would have a coupling with the sterile neutrino itself, right?
Yeah.
I see. Okay. Yeah, that's something that we didn't consider in this. So we did not consider those kind of interactions here.
I see. Because normally, if you consider gauged B minus L, people introduce 3 flavors of right-hand neutrinos to make it anomaly free. So that kind of UV I had in mind, but you didn't think of those.
Yeah, no. In this case, we just coupled it to the active neutrinos itself.
Okay, I see.
Yeah, so in some sense, yeah, the coupling to the sterile neutrinos we didn't consider. Yeah.
I see. Okay, thank you.
I have a question. Hi, Manibrata. Could you please go to this figure where the Dodelson-Widrow line opens up?
This one.
Yeah, this one. So in light of the new parameter space allowed by this new self-interaction, could you please comment a bit about how this new parameter space performs in light of the Lyman alpha bounds?
Oh, yes. So the Lyman alpha bounds, if you look at the traditional one, that rules out dark matter masses of order of 30 keV or so. So the reason why, so it would still be around 30 keV, but we didn't really do a more serious analysis with the Lyman alpha bound because first it's quite complicated, and secondly, we did not impose these bounds out here because what we understood from the literature was that the Lyman alpha bound still suffers from a lot of uncertainty regarding how the interstellar medium is modeled. So we did not really impose that out here. But if you believe the Lyman alpha bounds, then that actually rules out things up to tens of keVs or so.
Okay, then still some parameter space
Then
is
still
still
some,
allowed.
yeah, exactly.
Okay.
Yeah.
Okay. Yeah.
Okay, any other questions?
I have a naive question. You introduced the new interaction among the active neutrinos, right? So what if you introduce a new interaction of, some interaction of sterile neutrinos?
Okay, so
with some of the standard particles was, for example, dark matter, etc.
yeah, so if you introduce it within the sterile sector, it's actually easier to evade a lot of bounds because none of these bounds actually hold. So we are looking into this scenario right now. Some of this work has already been done for the case of a heavy mediator, where the mediator mass is kind of heavy. The only tricky part is that in that case, the whole system the numerical problem kind of becomes a little unstable. So what you end up seeing is that you go from a region of under density to a region of over density quite quickly, and it's very difficult to track down the region that gives you a relic density. So we are trying to look into that problem currently to see if you can actually do it. But there are recent works by George Fuller and company who actually look into this scenario for self-interaction in the sterile sector. If you don't want to care about dark matter, self-interactions in the sterile sector have also been used to solve other problems. But in that case, they're more interested in a case where the sterile neutrino is of the order of a few eV, and they want to look at the LFMB and the mini-Bohr nanometer.
Okay, thank you.
In the previous figure, you show the relative lines. I think one before that, where you show that the region which is overabundant in the S line.
Oh, this one. Yeah.
Yeah, this one. So usually the lines for relative abundance goes like in a different, opposite direction compared to direct detection. That means that, for instance, for very small couplings and large mass, the dark matter would basically decouple too early and be overabundant. However, here is different, right? So you have a region which is underabundant for very small couplings and large mass. This is because you start with low abundance of the sterile neutrino. That's just that.
So one reason is, of course, because we start with a lower abundance, but also it depends on how the interaction works, right? So if you are in this regime, so you are basically in a regime where the coupling is low and the mass is high. So these interactions are not at all quite effective, which is why you don't end up producing so much of dark matter. In this regime, on the other hand, the mass is low, so your overall effective coupling, which goes like lambda square over m square, is quite large. So that's why you end up over producing it. Again, this is dependent on ms and sterile angle. If you change that, this region changes.
Thank you.
Okay, any other questions or comment?
I had one just out of curiosity about the Dodelson-Widrow mechanism. So it's basically the sterile neutrino is produced from the oscillation, but we can think of that production as a freeze-in type of process.
Yes.
So that the electroweak interaction gives the producing the sterile neutrino directly. So there's a sort of additional contribution. Is that right?
Yes, so it's freezing, but then you have the oscillations also. So it's not just freezing through interactions itself.
Yeah. In addition to the oscillation,
right.
There's a freezing
process
from the annihilation with some number of particles.
Yes. So yeah.
I'm talking about the Dodelson-Widrow mechanism, not introducing.
But even in the Dodelson-Widrow mechanism, this is a freeze-in process. So what happens is, this interaction basically freezes in the sterile population, because every time the interaction happens, the active component is reset, and gradually the sterile population builds up. So it kind of builds up and then it plateaus.
Yeah, I know. But my question is, the sterile neutrino as a mass basis has a direct coupling to the standard model, like in this picture, the stray neutrino is produced from the oscillation from the active neutrino. But if you rotate the basis, field basis into a mass basis, the stray neutrino also couples to the standard model, which is proportional to the mixing angle.
Right. Yes.
And for instance, the annihilation of the, for instance, UD bar into lepton and stray neutrino. And we can think of this as a freeze in annihilation process to give a dark matter, and like additional channel. So I'm just wondering if this is, it's negligible compared to the oscillation contribution, or
No,
for any reason.
So if I understand your question, I think you are referring to regimes where what you're saying is right, but then that requires, so if the contribution is appreciable, that requires your mixing angle to be larger. So for that reason,
maybe.
Yes, so that ends up, what that does is that ends up thermalizing the sterile neutrinos with the active neutrinos before BBN. So that is automatically ruled out. So you don't want the sterile neutrinos to be thermalized with the active neutrinos before 1 MeV. And if you have a very large mixing angle, then you produce a lot of sterile neutrinos and it gets thermalized with the active neutrinos before 1 MeV. So that's why you have to go to smaller angle and produce them non-thermally through this freezing that we see.
And then eventually the oscillation dominates production.
Yes.
Yeah, I see. All right. Thank you.
Could you go to the intermediate region?
This one, right?
No, the M5 is
this one.
The total curve is shown.
Sorry, which the total composition as
yeah.
This one or this one? Could you tell me
the S curve and
this one?
No, next maybe. Next.
Oh, do you mean this?
Yeah, this one.
Okay.
Could you explain a little bit more about this density region?
Oh yeah, this is.
So you said this part is very difficult.
Yeah. So essentially, anything above this region is something that I explained just before. So you have a heavy mediator and nothing thermalizes before BBN. So you calculate your relic density as it is. Anything slightly below this region is where you start with so the way we do this calculation is we have a negligible amount of phi just slightly above BBN. And as BBN happens, phi starts getting into thermal equilibrium with the neutrino sector. So then again, you have constraints from delta N effective, because once phi decays again into neutrinos, it changes delta N effective at around CME. So we understand this sector as well. It's around 1 MeV where the phi gradually starts attaining thermal equilibrium with the neutrino sector, and the neutrinos also start decoupling. Now, neutrino decoupling is not really an instantaneous process. We can approximate it by an instantaneous process at around a few MeV, but that takes quite a long time because there are interactions with the electrons, scatterings with the electrons and all that still keep on going. So the cosmology that governs the part out here and the part out here are quite different. So we did not really try to connect these two so it's not fair to extrapolate this line and connect them. So there is something more complicated going on out here, which needs much more refined analysis, which we did not do out here, which is why we put this thing as a dashed line. We expect, you don't expect something drastic to happen out here, so it will probably be like this, but we did not really estimate this part.
Okay, any other questions? If there is no more question, then let's thank to Manibrata-san. Thank you very much.
Thank you.
Could you send your slide to email?
Yes, I will do that. Yes.
Okay, thank you very much.
Thank you.
Bye-bye.